All right. Good morning. So we're going to try to start early today um so we can complete chemical kinetics and go to chemical equilibrium. Now, the last class, I was actually I think I finished explaining this, but I want to believe that maybe I kind of like explain it in a hurry a bit because time was already fast spent. So what I was saying that day was that this is the first example, or maybe we need to take it from here. That when you, for integrated rate law, if you want to, what you use it to do is to confirm whether a particular reaction follow a particular order. That is what you do. You're not calculating order of reaction. You just want to check whether your concentration time data follow a particular order. Remember, I said that for integrated rate law, you need concentration time data. While for differential rate law, you need concentration rate data. But even sometimes when you have concentration time data, you can calculate your rate and use differential rate law. But we're not trying to do that here. At this level, when you see concentration time data, concentration rate data, you should follow what I said accordingly. Now, okay, now with concentration time data, that means more often than not, you expected, or the question will tell you to prove or show or check whether that particular reaction follow a particular order. And I told you, yeah, this is the differential rate equation for zero order. This is integrated rate law. And for integrated rate law for zero order, that means that if you plot concentration against time, you should get a straight line. But of course, it's just going to be like an horizontal line anyway, because you're not going to be having any change in okay, sorry. You're not going to have you're going to have a straight line, sorry. Not horizontal, you're going to have a straight line. But the fact that you have a straight line, what that means is that the rate is actually not, the rate is not changing. The rate is not changing in that situation, because remember, you're plotting concentration against time. So on a normal day or normal reaction, when you plot your concentration against time, you should have a curve, not a straight line. So, but when you now have a straight line, what that means is that you have a zero order reaction. And if you want to calculate the half-life for that particular reaction, this is the formula. Now, for first order reaction, this is the integrated rate law. And of course, you're plotting the ln of concentration at any time against time. For a first order reaction, when you plot the ln of the concentration you're given against the corresponding time, you must have a straight line, while the slope of the curve is going to be your rate constant. And you want to calculate the half-life of that reaction, that's going to be the ln 2 divided by the rate constant. For second order reaction, you're plotting the reciprocal of concentration at any time t against the corresponding time. And that also should give you a straight line. And now, this now happens to be our first example. And again, something that I said also was that when you're getting a straight line, that means your slope is the same. That's what it means. Whatever you plot and you're getting a straight line, that means the slope of that particular curve is the same. If it's not the same, you won't have a straight line. You'll have something that looks like a curve. Now, the fact that you have, we're talking about having a straight line. There's also something that means also, which we need to know. It's not just all about us getting a straight line. What does it even mean when you're getting a straight line? It means that for every step of that reaction, if it's a rate constant, irrespective of what the concentration is, the rate constant must be the same. Now that means that it doesn't matter what part of the data you're using, your K or your rate constant must stay the same, or they must be approximately equal. Meaning that there are two ways of doing this. You either plot a graph and you expect to get a straight line if the reaction follows that particular order, or you can calculate rate constant for few of those steps. You can calculate for 95 seconds, calculate for 140 seconds, calculate for 222 seconds. if you have rate constant that are approximately the same, that is telling you the same thing, that, okay, this reaction is a second order reaction. Because what that means is that if you plotted it, you still get a straight line. And now, my explanation of this was that, because I know students, I'm using this because students always have like, okay, but what we have here is milliliter, not concentration. And we're expected to plot concentration. But you need to look at the question very well. The hydrolysis of ethyl nitrobenzoate by aqueous sodium hydroxide was followed at 25 degrees Celsius by titration of the hydroxide against standard acid at different stages in the reaction. From the given data, show that the reaction is second order. Now, what this means is that the meaning of this, you have ethyl nitrobenzoate and aqueous sodium hydroxide as your reactant. Now, you monitor the reaction using what is called a classical method. That is actually not using what is called a classical method. That is, you are now titrating the sodium hydroxide with a standard acid to know the amount of sodium hydroxide left. Now, remember, as the reaction progresses, sodium hydroxide will be consumed, meaning that the concentration of sodium hydroxide is expected to decrease in the course of the reaction. Now, what that means is that as you titrate your sodium hydroxide with standard acid, the volume of acid you're going to be using should also drop, because the concentration of sodium hydroxide is falling in the course of the reaction. Meaning, as the reaction progresses, the amount of sodium acid you're going to be using is also going to drop. Now, and the amount of acid, the way it falls is also going to be proportional to the fall in concentration. Meaning that you can use your volume in place of concentration because it's directly proportional to it. And again, even when you want to divide, what you're going to have, if you use volume, if you use concentration, you're going to be dividing concentration with concentration. So you can use volume, because at the end of the day, it's still going to amount to the same thing. And that's why nobody's talking about concentration in this reaction, because concentration is actually not needed to be able, it doesn't mean it can be supplied, but it's not needed to be able to arrive at what you want to use. You can use your volume in place of concentration. And now this is now what you are. Like I said, we didn't use graphical method here because since we're going to be doing CBT, so we feel that, okay, we also need to kind of, I already said it, you want to do a plot, so you're in 100 levels. So this is not, I'm sure you learned how to plot a graph. You're plotting reciprocal of 80 against time, and that should give you a straight line. That's the graphical method. Now, the calculation now, if you just want to do it by calculation, that means you have 95 degrees. You're starting from 0 anyway. But 0 is actually not here, because essentially what you're going to have is just going to be 0, 95. Then you have 10, 9.3. But normally, I think I should have actually just added that to that, because we needed the A naught itself, which is, what is that A naught now? Okay, yeah, sorry. Remember, the A naught is 10. And you're subtracting 80 from A naught. This is your 80, which is 93. This is, the time here is 95. Remember, the first time is 0. Our A naught is 10. Now, the second time is 95 seconds. Our 80 now, because you're no longer at A naught, which is the initial concentration. Our 80 now will be 9.3. And that's why your A naught minus 80 is equal to 0.7, because that's 10 minus 9.3. Then you do, so for that data, you can do your calculation. You can calculate your K. 0.7 divided by A naught multiplied by 80, then divided by time. And that gives you 7.92 seconds. You go to 140 seconds also. In this case now, your A naught is still 10 minus 9.0. That will give you 1.0, as you see here. Then you also have 10 multiplied by 90, which is your A naught multiplied. What you're subtracting here is what you're multiplying. So which gives you 90. Then you calculate your K, that gives you 7.93, and so on. That's what you do. Now, if you look at all these values for K, you realize that they are approximately equal. They can be said to be approximately equal. What that means is that if you had plotted a graph of reciprocal of 80 against time, you would have gotten a straight line. Meaning that we can conclude from this calculation that this reaction, this data set follow a second order reaction. Now, for half-life, of course, half-life of a reaction is actually the time required for the concentration of reactant to drop to half of its initial value. If you're starting from 10 molar per molar, how long does it take you to get to 5 molar? That's your half-life. You're starting from 2, how long does it take you to get to 1? That's your half-life. So that's what we mean by half-life. And of course, half-life also came out half-life for each of this. We're not doing derivation like I said. Half-life for each of this came out of the integrated rate law. What you did for half-life, if we're saying that for half-life, it is the amount of time it takes for the original concentration to drop to half. You can get this half-life by just substituting A naught divided by 2 for your AT, because that's what your AT means. Remember, your AT is concentration at any time T. And that means that half-life, which is also a time T, at half-life, your AT is going to be A naught divided by 2. If you put A naught divided by 2 here, you're going to end up with this. The only difference was that to signify that we're dealing with half-life, we no longer write T, we write T subscript half. That is telling you that half-life at T subscript half, your AT is going to be equal to A naught, which is the same for all the equation. You do the same and you end up with the half-life expression. So now, okay. I thought we had examples for half-life. Okay, but we don't have example for half-life, but I think maybe I'll try to bring examples next time. But again, I remember now that I said, before we move to, I remember I said I still had something to say on pseudo-order reaction. So let me quickly go back to that because I wouldn't want to just move on without talking about that. Now, we've spoken about it anyway, and I just needed to kind of like create a little bit of for a better understanding. Remember that the concept of pseudo-order actually came from the fact that we're trying to determine order of reaction. Though, of course, it goes beyond that. But for this level, that concept came from the fact that we're trying to determine order of reaction. And if you have a reaction where you have 2 reactants, you want to determine the order with respect to a particular reactant. Now, one of those things you do is you hold the concentration of one, of the other one constant. You hold the concentration constant. And one way of holding that concentration constant, remember we spoke about, okay, you can, just like I showed, we did in this table, where, remember, we held B constant here because we carried out series of experiments. But another way, rather than carrying out a series of experiments, is to use excess of one reactant. Of course, the individual, therefore, at the research level, they are for different purposes anyway, but at the end of the day, it's still about order of reaction. But your goals are a little different. But like I said, that is not for this class. The most important thing, both are actually used when it comes to determination of order of reaction. But in this case, you are series of reaction because you're trying to you want to measure this at 1.0 and again at 1.0 while you measure A at 1.0 and 2.0. That is you keeping the concentration of B constant while doubling the concentration of A. And of course, you measure the initial rate. But in the case of this is not a pseudo-order situation. This is not a pseudo-order situation because I know that students do get this confused that, okay, but you have a pseudo-order where you're running just an experiment or you're carrying out your reaction at a go, and you now have the concentration of 1 in excess. You have the concentration of 1 in excess. What that means in excess is that you you have the, say for example, if wine is a 0.2 molar, and you have the second one, the second reactant, the concentration is now like minimum of 10-fold of the first one. Say one is 0.2 molar, you have the second one at 2 molar. Now that is in excess. You can assume that is in excess. And why do we call it in excess? And remember, and if we're saying it's in excess, why do we say that, or why do we still say that the concentration is constant? The concentration is constant because at the end of the reaction, remember, A only has 0.2, B has 2 molar. At the end of the reaction, when A is completely consumed, say 0.2, especially if we're dealing with a 1-to-1 mole ratio reaction. By the time A is completely consumed at 0.2, that means you're still going to have 1.8 molar left for B. And 1.8 molar can be safely approximated to 2. So that means that essentially you can assume that that concentration was constant because the change you have in the course of that reaction was very, very negligible. The change you have in the course of that reaction was very, very negligible. So it's an assumption or based on reality, really. Because and again, you can have something like 0.05 and the other one is 1. That means that at the end of the reaction, when the 0.05 is consumed, you're still going to have 0.95 of the other one, which is approximately 1. And that's why you say that, okay, the concentration of B, or the one whose concentration is in excess, is a constant. Now, remember we have AB, we are having B in excess now, while we monitor the order of reaction with respect to A. Meaning now that we can now just use our integrated rate law that we showed the other time with the concentration, because you can just monitor the concentration of A with time. When you monitor the concentration of A with time, you can now determine the order of reaction. Is it first order? Is it second order? Now, whatever order you get for A can now be said to be the order of the whole reaction. Now, that's not correct. That's false. False in the sense that there is a B who also has his own order. But we can't monitor his own order because his concentration is not changing. So because his concentration is not changing, we now assume that his concentration is constant, and therefore we can add his concentration to the rate constant. We can add his concentration to the rate constant. So that, but instead, for example, your order with respect to A in the course of that reaction is first order. Now, you can now say the reaction is a pseudo first order reaction. Pseudo first order because we ignore the order of B. Pseudo because we ignore the order of B. If A is second order, we can now say the reaction is pseudo second order. Pseudo because we ignore the order of B. You can do the same thing with A you can do the same thing with B while you keep A in excess and constant. So that is the whole idea behind the concept of pseudo-order reaction. Now, and like I said, so pseudo-order reaction in which the reactant B is present in large excess, since it is an elementary reaction, the rate law can be written as this. As B is present in large excess, the concentration remains practically constant in the course of the reaction. Thus, the rate law can be written as, this is a capital K, mind you, this is a small k, this is a capital K. Now, Ka. Now, your capital K now is equal to your small k, multiply your concentration of B. Okay, sorry, I'm not sure what this T is doing there. It shouldn't be there, please ignore it. So your small k, sorry, your capital K is equal to your, so this rate constant is your pseudo-order rate constant. The K is the normal order, is your real rate constant, while the capital K is your pseudo-order rate constant. If the order with respect to A is first order, that means this is your K is going to be pseudo first order rate constant. If the order with respect to A is second order, that means your capital K is going to be your pseudo second order rate constant. But of course, you can calculate the real order of reaction, but that is beyond the scope of this class. We just needed to, because in 200, sorry, even I think it's in 300 level, that's when you actually get to talk about, okay, how do we even calculate from that process, how do we calculate our small k? Now, this is a good example of that. We're not talking about the calculation, but we just want you to see what we're talking about. Now, example of pseudo-order reactions, hydrolysis of methyl acetate in aqueous solution. Now, this is a very slow reaction, but again, to make it fast, a small amount of mineral acid is normally added as a catalyst, and you have this reaction. But the real rate of reaction, this is the real rate of reaction, because you want to write a reaction for this. The reaction is first order with respect to ester, also first order with respect to water. But since you have 1 mole of water, 1 mole of you have 1 mole of water, 1 mole of water. Now, but in this kind of reaction, remember, you're talking about aqueous solution of this ester of methyl acetate. Now, you know, if you're talking about aqueous solution, that means you're going to have water in it. That means you can't even talk about concentration of water in this case, because you already have water in excess. It doesn't matter what ethyl acetate is doing, the amount of water you're still going to have unreacted is going to be very, very large. That means in the course of this hydrolysis reaction, the concentration of water can be assumed to be constant. Can be assumed to be constant because only very little amount of water is going to react, and you have very large amount left. So the only thing you do here is you just monitor the concentration of the methyl acetate. And therefore, this reaction, or this K1 that you've written here, it's a pseudo-order rate constant because we completely ignored water, or we completely ignored the order of concentration of water. It's been added to this K1 because it's a constant. Remember, K1 is also a constant. Sorry, our K is also a constant, and that's why it's added to give you K. Now, sorry, there's a mistake here. This K1 should have a prime because these are not the same K. Sorry, remember the other time I said that your small k multiply your concentration of B equals your capital K. The same thing still holds here. These are not the same K. I would rather call this one K1 prime. I would rather call this one K1 prime. And now, the rate of reaction is determined only by the concentration of the methyl acetate, and hence this reaction is of the first order and obey first order rate equation. Now, of course, these reactions are referred to as pseudo-unimolecular reactions. So that is what I really wanted to talk about concerning the pseudo-order reaction, so that we can actually have a better clarity. Now, what we have left under our because there are two parts to this. We have the chemical kinetics part and also the chemical dynamics. The chemical dynamics. Now, this is the chemical dynamics. And now this talks about the collision theory of reaction rates. Really. We know that according to that reaction, you can only have a reaction when reacting molecules collide. But not all collisions are effective. You see, you can have collision, but it doesn't mean that all those collisions, we say to have reaction, there must be collision. But it doesn't mean that all collision will result in reaction. That is only small fractions of your collision produce reaction. Now, what are the reasons? Why is it that not all collisions lead to reaction? Now, there are two things. For collision to be productive, two conditions must be fulfilled, really, must be met. Now, they must possess sufficient kinetic energy to cause a reaction. There is an energy barrier that must be crossed, really. So the collision must have at least the minimum that collision needs to, the minimum energy the collision needs to be able to become a reaction or to lead to reaction is that energy barrier. That kinetic energy, that's the minimum. Now, the reacting molecule must also collide with proper orientation. We don't want to go into detail of that, but those are the two conditions. Energy, orientation. If any of this is missing, of course, that collision might not, even when it has sufficient energy, if the orientation is not right, you can even have repulsion. They look like they collide, but they're not collide. They're not going to stick together. They bounce off each other because of the wrong collision. Say you have a two electron-rich area approaching each other. You need an electron-rich area and an electron-deficient area to approach each other to be able to have a reaction. But you are now having a two electron-rich area approaching each other. Of course, you can't have a reaction. That's wrong orientation. And You need those two. Even if the orientation is correct, if the energy is not sufficient, you can't have a reaction. Now, so these are the okay. I think I already well. You see, that's the thing. What we have there already explained. Anyway. So, but again, let's just read it. That what I just explained now. It's what we have here. I should have just come here before. Now, activation energy is the minimum energy necessary to cause a reaction between the colliding molecules. Only the molecules that collide with the kinetic energy greater than EA are able to get over the barrier and react. The molecules colliding with kinetic energy less than EA fail to surmount that barrier. Now, the second one, which is the orientation, the molecule must collide with favorable orientation. The correct orientation is that which ensures direct contact between atoms involved in the breaking and forming of bonds. So you need those two conditions to be met before you can have a reaction. But now, another important concept when you're talking about this is the fact that temperature also has a significance, because we just spoke about collision now. For you to have a reaction, there must be collision. But not all collision leads to reaction. But for collision to lead to reaction, there must be enough kinetic energy to surmount the energy barrier known as the activation energy. Then there must also be the molecule must also collide with proper orientation. But again, even you see now, because you're talking about collision, to make collision happen, temperature is also important. Because remember, when you heat something up, they gain kinetic energy. When they gain kinetic energy, that's when they begin to collide. And that's why we said that temperature has got a significant effect on the rate of reaction. Now, of course, it has been observed experimentally that increase in temperature leads to remarkable increase in the rate of chemical reaction, and hence even the rate constant itself. And that is why, remember, we mentioned that also, that rate of reaction remains rate constant does not change with concentration, but it changes with temperature. Rate constant does not change with concentration, but it changes with temperature. That is why you do not use rate constant. You don't use concentration to compare two reactions. You can't be saying, okay, I want to compare reaction A and B, and you're looking at concentration. No, because even for each of those reactions, the rate will be different at different concentration. But rate constant is expected to be the same, irrespective of what happens to concentration. But it changes with temperature. So, and that's why we said that, of course, that increase in temperature leads to a remarkable increase in the rate of reaction, and hence its rate constant. Now, the relationship between the energy barrier to the reactions. Now, that means that it was saying that temperature affects the rate at which a reaction happens. And it's rate constant, not just because we also need to mention rate constant. Remember, concentration also affects the rate, but not rate constant. That's why the important thing here is that temperature affects rate constant. Now, for it to affect rate constant, that means it affects the rate. Now, how does it affect the rate? For it to affect the rate, that means it must affect one of those things, the major thing that affects it, which is collision. Meaning that if you increase your temperature, of course, you have higher the kinetic energy increases, and therefore the number of collision also increases. But now, and that means that, but again, that you're increasing the number of collision is not the issue here. But is the kinetic energy enough to surmount that activation energy barrier? That is what is important. Is the kinetic energy enough? Because you're increasing the number of collisions. But again, that's not the issue. How many of those collisions actually have enough energy? Do they have enough energy to be able to surmount that energy barrier, which we call the activation energy? And that is why there has to be a relationship between temperature, rate constant, and activation energy. And that is the temperature. That is the equation that you have here. In this case, now you have your K as a rate constant, A as the Arrhenius factor, EA your activation energy, R your gas constant, YT is your absolute temperature. Now, of course, the A, okay, so sometimes we also call the A the frequency factor. So the constant K and EA are related to, of course, your A and B. Hold on. So the factor A is known as frequency factor. So you can rewrite that equation, and by just if you want to remove that exponential, then you get this really. So that means that if you plot the log of k against the reciprocal of time, you will have your activation energy divided by 2.303. You can do lean anyway, but of course we have it as log here. So your activation energy divided by 2.303. Remember, R is a constant. Okay, a plot of log K versus reciprocal of T should be a straight line with a slope of minus EA, 2.303 R. T is not there, please. That thing should just be, remember, you're plotting against reciprocal of T. So that T should disappear from the slope. It's not part of the slope. And you're going to have your intercept as log A. And of course, you can use this to, meaning that you can calculate the activation energy. You can calculate the activation energy of a reaction by determining your rate constant at different temperature. That means you can calculate the activation energy by determining your rate constant at different temperature. If you do that, that means you can have log K. What is your rate constant at time 1, your rate constant at time 2, your rate constant at time 3, and so on. And you can now plot the log of your rate constant against the reciprocal of your, of your time, really, of your temperature, not time. I kept saying time, temperature. Against the reciprocal of your temperature. And of course, you can get your activation energy. Since your gas constant is a constant, then from your slope, you can get your activation energy. Now, okay, and that's what you have here, that if you know the slope, you can now calculate your activation energy. Now, for the decomposition of N2O5, if the slope is minus 5,400 kilojoule per mole, oh, sorry, I think it's actually written as, okay, cal per mole, really. So hence, your EA, that means your EA, because if you have your, it's just all about making your EA the subject of the formula. Your slope equals EA minus EA divided by 2.303 R. Then you just make your EA the subject of the formula. And of course, that will give you, and that's why if you make your EA the subject of the formula, you're going to have your, okay, what am I saying now? Okay, where is it? What are we calculating here? We are calculating, okay, we're determining EA. So if you want to make your EA the subject of the formula, that means you're going to be multiplying the slope. You're going to be multiplying the slope by 2.303 R. You're going to be multiplying the slope by 2.303 R. So, and that's what, this is your slope, 2.303, then your gas constant here is 1.987. And that's how you end up with that 24,700 cal per mole. Now, EA can also be determined if you know specific rate constant at 2 different temperatures. This is one way of determining your EA. You can do a graph. You have series of temperatures, say 4, 5, or, well, the minimum you want to use for that is 4 anyway. In fact, the minimum should be 5, really, that you want to use for this kind of thing. So you have temperature 1, your rate constant, temperature 2, your rate constant, temperature 3, your rate constant, temperature 4, your rate constant, temperature 5, your rate constant. Now plot the log of your rate constant against temperature. But another one is you can use any 2 temperature. You know rate constant at any 2 temperature. Then you use this equation that we have here. What's going on here? Oh, okay. I think that's my fault. So if your rate constant at temperature 1 is T1, your rate constant at temperature 2 is T2, then you can still make your EA the subject of the formula from this equation and get your rate constant. Sorry, and get your activation energy. And again, it doesn't mean that, of course, you can be given activation energy out of the 2 rate constant, you're given 1 and you're given the 2 temperature and you're asked to calculate your K1. Or you can even be given activation energy K2, K1, and be asked to calculate temperature. But the most important thing is you understand what this formula is all about. This is the formula that relates 2 temperature with 2 rate constant and activation energy. Whichever one is your unknown in this one, you can always find as long as you know the rest and you only have one unknown. Now, this is an example for that. So you have a benzene diazonium chloride decomposes in the presence of water, according to the first order kinetics. If the rate constant at 25 degrees Celsius is 28 times 10 raised to the minus 3 per minute, and the activation energy is 11.9 kilocalorie per mole, find the rate constant at 35 degrees Celsius. Now, in this case, now you see this is what I'm talking about. You've been given the activation energy, you've been given the two temperature, but you're given one rate constant. You're asked to calculate the second rate constant at that particular temperature. So now, of course, you know your at T1, you know what your at T1, you know what your activation in what your rate constant is. At T2, we do not know what the rate constant is, sorry. But we know the activation energy. We know the activation energy, meaning that we can make it to the subject of the formula and just get our activation, get our K2 out. And this is what your K2 is from that manipulation. Now, that is where we stop for chemical kinetics. I already spent more than, I thought I was going to spend 20 minutes on whatever was left of chemical kinetics, and I already spent 40 minutes. Okay, now, so we can start our chemical equilibrium. That's the second topic. That is the second topic. Now, we know that, well, maybe more often than not, or 99% of the time, you have chemical reactions that most chemical reactions, 99%, even maybe 99.9%, they proceed in both ways. They proceed in both ways. That is, you have forward reaction, you're also having backward reaction. And that's what you have here. You have your A plus B reacting to give you C plus D. And C plus D is also reacting to give you back your A plus B. Now, but of course, if the products are not allowed to escape, if you're forming your A plus B, if your A plus B is forming C plus D, and C plus D is actually escaping, then of course, you can't have this kind of reaction. That means you need to have your C and D in a closed region where they can escape, really, where they can escape, so that they can actually undergo that reaction. If they escape, you're talking about a gaseous product that escape, and you allow, or you have just one gaseous product and one liquid product, and the gaseous product is allowed to escape. Of course, you won't have this, meaning that all this must be present together. That is, the products are not allowed to escape. Then as soon as they accumulate, they start reacting to form the reactant back. Now, you will expect your C and D to react under the same condition at which your A and B react, so that a stage is reached at which A and B give as much C and D as C and D react to give A and B. In other words, what this is saying, now, you see, what we're saying here is that A and B react to give C and D. C and D, as long as they're not allowed to escape, or none of them is allowed to escape, also react together to give you A and B. But now, of course, it doesn't mean that the reaction between C and D starts immediately. You need to really, because they have to accumulate up to a point. Remember what we said about concentration. Concentration rate decreases with concentration. When you have very low concentration of this, they can't even get in touch with each other, not to talk of collision. And if they're not getting in touch with each other, they're not colliding, there can be a reaction. But in this situation now, just a minute, I wanted to quickly check. I forgot to check our people online. What's going on? Oh, okay. Oh, okay. I was scared. I thought the YouTube wasn't working. Okay, now, okay, all right. So now what I was now saying is that at some point, you have enough C and D to kickstart a reaction between the two of them. So that reaction starts. Immediately the reaction starts, that means C and D, as A and B is forming C and D is also forming A and B. But you're going to get to a stage where the rate at which C and D is forming, remember at the beginning, A and B is going to be moving at a very fast rate. But that is because the concentration is high. Then C and D, when it starts, is going to start very slow because the concentration is low. As the concentration of A and B drops, remember the rate will also drop. As the concentration of C and D increases, the rate will also increase. The rate of the forward reaction will start dropping, while the rate of the backward reaction will start increasing until they get to a point where both of them are the same. Where both of them are the same. Now, at that stage, because that means the rate at which you're forming A and B is the same rate at which you're forming C and D. Then that means that the concentration of A, B, C, and D will remain unchanged. It does not mean that they are going to be, a concentration of A and B is going to be the same thing as the concentration of C and D. No. The concentration of A stays the same. The concentration of B stays the same. The concentration of C also stays the same, while that of D also stays the same. By virtue of the fact that the rate at which each of them is being consumed equals the rate at which they are being produced. And that happened because concentration, rate of the forward reaction dropped because concentration dropped. Rate of the backward reaction increases or increased because the concentration also increased. And they get to a meeting point. And that meeting point is what we refer to as chemical equilibrium. At that stage, the concentration of reactants and products are fixed. They are no longer changing. That is what is referred to as chemical equilibrium. And again, I'll repeat this because I know that because we had this issue the last time where students thought that, okay, we said that, okay, the concentration of the reactant equals, no. It doesn't mean that the concentration of reactants equals the concentration of product, no. The only thing it means is that the concentration of each of them stays constant. The reaction is still going on. A and B is still forming C and D. C and D is still forming A and B. But hey, the rate at which both of them are moving are just the same. And there are molecular exchanges, or there are exchanges, but it's not affecting the concentration because those rates remains the same. Okay. So at chemical equilibrium, no perceptible transformation can be observed in the system because you're not going to see any changes. Concentration stays the same. It's going to look like the reaction has come to a standstill, although in reality, the forward and backward reactions are proceeding at equal speed all the time. And that's why they said that equilibrium is dynamic in nature. Equilibrium is dynamic in nature. So under any given condition of pressure and temperature, the point at which equilibrium is established between the reactants and product is always the same. That is for a particular reaction. And that's why for a particular reaction, as long as you are working at the same pressure and temperature, your equilibrium constant will remain the same. So, and that's why they said that under any given condition of pressure and temperature, the point at which equilibrium is established between the reactant and product, they are always the same. Now, this is an example. This can be illustrated by considering a reaction between hydrogen and iodine in a closed vessel, which may be represented as that equation. Then at temperature of 425 degrees Celsius, the composition of the mixture is found to be 12% hydrogen, 12% iodine, and 76% hydrogen iodide. And it's because of this equilibrium. That's why they said some reaction, most reaction never go into completion because a lot of them seems to do this. Now, if the reaction is started with hydrogen iodide at the same temperature, we shall find that the same composition persists for the same equilibrium. It doesn't matter where you're starting from, whether you're starting from hydrogen iodide or you're starting from hydrogen and iodine, you still realize that you still end up with the same composition at equilibrium. Now, there's something called the law of mass action. And the law of mass action actually helps us to find the relation between, remember, the concentration we just spoke about now at equilibrium in the chemical reaction. The law of mass action helps us find the relationship between concentration of reactant and product at equilibrium in a chemical reaction. And this law says that at constant temperature, the rate at which a substance reacts is directly proportional to its active mass. At constant temperature, the rate at which a substance reacts is directly proportional to its active mass. The velocity of chemical reaction is proportional to the product of the active masses of the reactor. Now that thing we use here, the active mass in the above statement, of course, it's actually a thermodynamic parameter, where A here is the active mass in that equation where you have your your BA. No, sorry, A is equal to CF. That B is not there. It's given by A is equal to C multiplied by F. Please take note of that. It's given by A is equal to C multiplied by F. A is the active mass. C is that concentration that we all know. And F is what is known as the activity coefficient. Now, for reactions involving gases and solutions, that F is equal to 1. And you can, for those reactions, and those are the kind of reactions we're even talking about here anyway, that F is equal to 1. And your active mass is equal to your concentration. And so, essentially what we're talking about from that, when you're dealing with gases and solutions, your active mass is the same thing as your concentration. Now, this is the law of mass action. Okay, I think I need to solve, so I can take your questions. Because now we have the 9:49, so we're already 10 minutes. So, and I know that a lot of you must have questions. So we can, because we want to finish on time. And okay, so your question, raise up your hand, please. This is where we're stopping today. We're going to continue from here on what's now? So that's on Wednesday. I'm still not sure what's going to happen on Wednesday because I have a PhD viva to attend. Okay, now give me a minute. I'm trying to catch my breath. Okay, so let me go to pen so I can take your question. If I want to. Oh, okay. Okay. Owen, what is this now? Please unmute. Is it Owen or what is it? Owen,
yes. Good morning, sir.
Good morning. Your question, please.
Sir, please, on slide 59, you said that log K is plotted against the inverse of temperature.
Hold on, 59. Okay, this one, Abi. Okay.
Yes. Yes, sir. Is log K also ln K? Are they the same thing?
You put your ln, the 2.303, like go out of the window. So there's a difference between the natural log and the other one. So when you're using ln, you won't be having this 2.303.
Okay.
All right. So I know that some equations you have it as ln, but we have it as log. Yeah. So but well, I assume that, and I assume that you kind of like know the relationship between ln and log anyway. So
yes, sir.
Yeah, thank you. So, but yeah, thank you. So, okay. Next, Joshua, your question, please.
Okay, sir.
Yep.
So when you're talking about the rate of reaction, like in chemical equilibrium,
okay, and
talking about the reactants, how they begin their rate of reaction at a faster rates, and as the other time you're telling us about the rate of reaction, as rates increases from the reactants and down to the products, my question is how they are able to.
I no, there's no rate. There's no way you're going to have. Maybe we've always said, and I said it several times. There's no way you're going to have increase in rate from reactants. No, reactants is decreasing in concentration. So your concentration is going to be dropping. So there's no contradiction here. We're the one who ate something else. When you start a reaction, concentration of the reactant decreases. We know that's the fact that everybody knows that, okay, you start a reaction, concentration decreases. What happens to rate? Rate also decreases. Which is the same thing here. Rate decreases for reactants, it increases for product. And now there's going to be a midpoint where both of them are equal. I'm not sure what you mean when you sounded like that.
Yeah, I get this. I got this part. But
Okay.
still, yeah, I got this part of, okay, now these are the become equal. When
Ask
you
your
rate,
question straight, please.
the question is how, don't worry, I've gotten the chat. You've said it.
All right. So Tunde Okazaki, on mute, please.
Yeah, good morning, sir.
Morning.
Please, my own is actually not a question per se,
Okay.
and I just have some observations as about the exam is approaching.
Okay.
It was about the continuous assessment for the chemistry department. And secondly, sir, the slide, we've not been getting it, sir, for the chemical kinetic. Thanks,
Okay.
sir.
Okay. Don't mute. Hold on. It's Joshua B. I wanted to, because there's something I need to ask you. Now, the lecturers who taught before me, when did they give you the slide? Maybe I got the wrong information. I asked a question. The student that spoke now. Okay. Now I can't even address your question now, since you did not, because I thought that what I had. Okay. Any other questions? Since I think he asked a question and just left. Isn't that what happened? That's funny now. All right. So any other question? Adielogun, your question, please.
So about the slide, it's about the slide. They
Okay.
used to drop it immediately after the class. So we used to go through it. That's what we used to study.
No, okay. Okay, now what I'll do is this. I think normally I should drop it in that what is it called? That chat area, right? Ish. Okay. Who is that? I'm not even sure who is asking question here, because if you're not asking question, please drop your hand. Let me know those who want to ask question. So Adielogun, you want to ask a question because I still have your hand, or if not.
No, sir, it's about the slides. They used to send it to our course reps, so they used to share it to us.
Your course rep, Abi.
Yes, sir.
Okay, close rep. I know you. Okay, you can see my number in that chat area. Okay, that platform is actually for course rep. So I think I'll just drop in on that platform. So that's fine. I'll drop it before the end of today. So goodness, Oni.
Sir, good morning, sir.
Good morning.
Okay. So my question is also about the continuous assessments, like when are we planning? Because I heard we have to do it before the exams, and the exams are fast approaching, sir.
Okay. Okay, I think I'll find out from the coordinator. I'm not the coordinator. So I'll find out from the coordinator and get back to you. But okay, but I just want to be rest assured. It won't do anything that will be unfair to you. But I'll get back to you. I'll ask the coordinator for so I'll give you feedback. I hope on Wednesday. Oladokun Inyoluwa Deborah, your question, please.
Yes, sir. Good morning, sir.
Morning.
Sir, is there any formula for calculating first order reaction?
Now, that's a question that has been answered. But again, that's what we've been talking about all this while. Like I said, there are varieties of ways. But one of the ways through which we talked about, because you said, is there any formula? Were you in the first class or second class even? Because when you're asking me for a formula, what did we do in this table? Because I'm coming now. Because there are questions when students ask, you ask yourself, okay, were they even paying attention at all? Where is it now? Okay, so what were we doing here? We're calculating order of reaction, weren't we? So I don't know. I'm not sure. This is one way also you go through your material to get the answer to that question, because we did that. And I also said the second method is actually sometimes when you are to just show using this formula. To just show. There are other formulas, but hey, we don't want to overload you with all the formulas. In fact, there are varieties of methods really, but these are just the two methods we're interested in here. And the inspection method and the integrated equation method, where all you do is just to show that a particular data set conform with a particular order. So which I think we did really. And most of like 70% of our conversation since we started has been around that. So okay, any other question? Show that the
Okay, sir. Now that it was read to the activation energy formula, that log K2 over K1, is it log K2 over log K1 or?
Which one? This one?
Yes, sir. Yes, sir. Is that log K2 over log K1 or?
You see, that's one of those. Now, if I write log K2 divided by log K1, so isn't it the same thing as log K2 divided by log then K2 divided by K1?
Okay, so it's the same, sir.
It's the same, yes.
Okay. I just wanted to confirm. Thank you, sir.
The only thing you shouldn't make a mistake of is to think it's log K2 divided by or log K2 divided by K1. Now, that would be something else. But in this case, now what you have is log bracket open K2 divided by K1. Bracket closed. Okay, so that's where I'm going to stop. I'll see you next class.